Good afternoon, everybody. Welcome to the lecture 4 of module 4 on inverse dynamics in musculoskeletal modeling. In this lecture, we would be discussing about inverse dynamics method in more detail, and we will be discussing about solved problems using the inverse dynamics approach. Actually, this lecture is in continuation to the earlier lecture on introduction to musculoskeletal modeling. The focus of this lecture is on inverse dynamics method as applicable to musculoskeletal modeling, along with the solutions of some solved problems. Let us first discuss about the salient features of the inverse dynamics method as applicable to the musculoskeletal modeling and analysis. As applicable to musculoskeletal modeling and analysis. A movement can be described by a large number of kinematic variables, displacements, joint angles, velocities and accelerations. With the musculoskeletal model and accurate kinematic data, we can predict the net joint forces and moments due to the muscles that cause the movement. The inverse dynamics method is a useful method to estimate variables such as joint reaction forces and moments of muscle forces. Individual muscle force can be estimated using an optimization method once the net joint moment due to the muscle forces are known. This would be discussed in the following lecture. An overview of the inverse dynamics method as applicable to rigid body dynamics of musculoskeletal system is presented in this slide. Segmental displacements are calculated from marker position data, and the marker position data is obtained from the 3D motion capture system. Thereafter, segmental velocities and accelerations are obtained using numerical differentiation. Knowing the segmental properties such as mass, length and moment of inertia from anthropometric data and ground reaction forces from force platform and segmental kinematic data as calculated earlier, we can actually obtain joint forces and moments using the equation of motion. So, the segmental mass properties, the ground reaction forces and the segmental velocities and acceleration, that is segmental kinematics, all three in combination with the equation of motion can be used to find out the joint forces and moments. Let us now consider the link segment model. We have discussed about this in the introductory lecture 4.1. As discussed in the earlier lecture, the anatomical segment of the body, say for instance a leg, can be represented with rigid segments. This mathematical model of the rigid segments is known as the link segment model, as indicated in the figure. Each segment is characterized by the mass and moment of inertia acting at the center of gravity of each link. So, together we can call this as a link segment model. The intersegmental forces and moments, as you can see here, the intersegmental forces and moments can be calculated using the free body diagram of each segment after isolating each member from the link segment model, similar to the frame structure in engineering mechanics. Furthermore, the intersegmental forces and moments can be calculated using the equations of motion and the inverse dynamics approach. Now, you can see here that we have 1, 2, 3 segments when we isolate the body from the link segment. Typically, we are taking out one segment and we are drawing the free body diagram of the segment, and the reaction forces at the joints and the moments are indicated for one segment. Now, if you consider this part of the free body, if you can assemble these 3 segments, you will actually end up in getting back the link segment model as indicated in the figure. Now, let us consider the first example of one problem that we are going to solve now. So, in a free body diagram of a link segment model, few known variables and some unknown variables are presented in this slide. So, the known variables are the acceleration of the segment COM, AX and AY, the angle of the segment in the plane of movement, the accelerations AX and AY is indicated here. The alpha is the angular acceleration of the segment in the plane of the movement. The Rxd and Ryd are the reaction forces at the distal end of the segment, as you can see here in the figure. So, we consider this as the distal end and the top end as the proximal end. Md is the net muscle moment at the distal joint. Okay. Usually determined previously from an analysis of the proximal muscles acting on the distal segment. Now, the unknown variables are on the proximal side, which is indicated here in this part of the figure. So, Rxp and Ryp are the reaction forces acting at the proximal joint, and Mp is the net muscle moment acting on the segment at the proximal end. Now, let us come to the problem definition of example number 1. So, we first assume that this is a static problem. So, we assume a static condition and a person is standing on one foot on a force platform or a force plate. The ground reaction force is found to act at 4 centimeter anterior, as you can see here, to the ankle joint, 4 centimeter anterior to the ankle joint. The ankle joint center is indicated and I had rounded it off. Note that the ground reaction force Ry1 is always acting upwards conventionally. The horizontal reaction force Rx1 is acting in the positive direction towards right, and the mass of the subject is given as 65 kg and the mass of the foot alone is 0.9 kg. So, we are supposed to calculate the joint reaction force and the net muscle moment around the ankle. So, considering a static situation, Ry1 is obviously equal to the body weight, but acting opposite in direction to the body weight. So, it is 65 m and g. So, we get 637.65 Newton as Ry1. Now, let us actually consider the free body diagram of this problem. As you can see, the Rx1 is actually acting in the positive direction towards right, Ry1 is vertically upwards, the C is the center of mass of the foot through which the body weight is acting, and it is actually acting 6 centimeter from the line of action of Y2, or rather Y2 is the reaction force at the ankle joint center, which is at a distance 6 centimeter from the center of mass of the foot. So, 6 centimeter, 4 centimeter are all given data, and you can see the other reaction force at the ankle joint given by Rx2 along the horizontal direction towards right, and we assume M2 the net muscle moment at the ankle joint. So, this is the center of the ankle joint as indicated in the figure. So, let us come to the solution. Step number 1, we again consider the free body diagram of the foot, and considering the free body diagram and considering force equilibrium along the x direction, summation of all the forces along x direction is equal to 0. So, the only two forces Rx2 and Rx1 are acting along the x direction. So, sum of these two should be equal to 0. So, each of them is equal to 0, Rx1 equal to 0 and Rx2 is equal to 0. Note that this is a redundant calculation considering static condition. Let us move to step number 2. We calculate the reaction force Ry2 along the vertical direction. So, considering again the free body diagram and the force equilibrium along the y direction, summation Fy is equal to 0 considering static equilibrium, and we write down the equations Ry2 plus Ry1 and Mg is acting downwards. So, when we substitute the value of Ry1 and Mg, we actually can calculate Ry2 as minus 628.83 Newton. Okay. So, the third step is by considering moment equilibrium about the COM, that is C. So, we consider the sum of the moments about the center of mass of the foot and we calculate M2. We first form the equation of the moment. As you can see, M2, Ry1 and Ry2 are taking part in this equation and M2 can be calculated as minus 24.97 Newton meter. Please note the negative sign here. The negative sign signifies that the muscle moment acting on the foot at the ankle joint is clockwise. The center of pressure of ground reaction force is acting 4 centimeter anterior to the ankle joint. Please note that. So, for this configuration, the moment at the ankle joint is calculated to be in a clockwise direction instead of an anti-clockwise direction as indicated in the figure. Let us discuss the second example on inverse dynamics method. So, let me define the problem here. From the data collected during the swing phase of the foot, we are asked to calculate the muscle moment and the reaction forces at the ankle joint. The given data are the subject's mass 65 kg and the limb segment length between ankle to metatarsal length, that is the link segment length is mentioned as 20 centimeter. So, the inertial characteristics of the foot can be actually calculated based on the anthropometric data which are given here. The segment weight, the mass is calculated in terms of the body weight, 0.9425 kg is the segment weight. The center of gravity position is indicated here, rho 0, and it is related to the length of the limb segment, that is 0.20. So, the center of gravity is located at a position 0.095 meters. The inertia, moment of inertia can be calculated as a product of the mass and the radius of gyration squared. So, it is calculated as 0.00850 kg per meter square. The angular acceleration alpha is assumed as 21.69 for this problem. Please note that this problem is on dynamics of the foot. So, we will be considering dynamic equilibrium condition, and it should be also noted that the foot is in the swing phase. Therefore, the ground reaction force on the foot will be 0 since the foot is in air during the swing phase. Now, let us come to the problem, the free body diagram of the foot, as you can see, is presented here on the left during the swing phase, showing the linear acceleration of the center of mass and the angular acceleration of the segment. So, 21.69 is the angular acceleration, whereas the linear acceleration Ax is 9.07 and minus 6.62 meters per second square Ay, that is along the vertical direction, the linear acceleration. So, we need to now calculate the three unknowns Rx1, y1 and m1 from the given data and the condition. Let us consider the solution of the example 2. Please note that this is a dynamic problem. Okay? So, we will be considering dynamic equilibrium along the x direction, y direction and the moment due to rotation about a joint center. If we write down the equation considering dynamic equilibrium along x direction, so summation of Fx equal to mass of the segment and the linear acceleration Ax. So, we can calculate Rx1 as 8.54 Newton. Considering dynamic equilibrium along the y direction, we can actually write summation Fy is equal to the mass and the acceleration, linear acceleration along the y direction. So, summation Fy is equal to m into Ay. So, if we write down this equation, we can actually calculate Ry as 3 Newton. Now, considering moment, so this is rotation about a joint center at the center of mass. So, we are taking moment about the center of mass of the foot. So, summation of mc is equal to I alpha. Okay? So, the left hand side of the equation is written that consists of m1 Rx1 and Ry1, whereas the right hand side of the equation, so this is the left hand side, the right hand side of the equation corresponds to I0 alpha. So, we put the value of I0, we put the value of alpha here in the equation and the values of Rx1 and Ry1 calculated just earlier, we can actually calculate m1 as 1.08 Newton meter. Let us discuss about some observations on the results obtained from the example 2. The horizontal reaction force Rx1 calculated as 8.54 Newton at the ankle joint is the cause of the horizontal acceleration calculated for the foot segment. So, the horizontal acceleration is indicated in the free body diagram just for clarity. During the swing phase, that is after toe off instant, the foot is actually moving upwards against gravity. That means the foot is decelerating. The vertical reaction force Ry1 equal to 3 Newton at the ankle joint is actually less than the static gravitational force of 9.45 Newton. And the third important observation from the problem is the ankle muscle moment calculated as M1 equal to 1.08 Newton meter as indicated in the diagram is positive. It is acting anti-clockwise or counterclockwise, indicating net dorsiflexor activity due to the muscle tibialis anterior. Let us now discuss another problem. This is example 3 of this lecture. In this example, we consider the same time instant as the example 2. We need to calculate the muscle moments and reaction forces at the knee joint. In example 2, it was on the ankle joint, but here in example 3, we will be finding the muscle moments and reaction forces or joint reaction forces and moments at the knee joint. The leg segment is given as 43.5 centimeter long. So, again, based on the anthropometric data, the segment weight, the limb segment weight can be calculated in relation to the body weight of 65 kg. So, it comes out to be 3.72 kg. The center of gravity position can be also calculated based on the length of the leg segment. So, the center of position comes to 0.131 meters, and the moment of inertia can be calculated based on the mass and the radius of gyration, and it comes to 0.0638 kg meter cube. So, all these variables can be actually calculated from the anthropometric data. The angular acceleration alpha is assumed to be 36.9 radians per second square, and from example 2, we will use the magnitude of the ankle joint reaction forces and moments. Ankle joint reaction forces and moment, Rx1 equal to 8.54 Newton, Ry1 3 Newton, and M1 as 1.08 Newton meter. Let us now discuss about the third example. Now, this example is based on a free body diagram of a leg at the same time instant as the foot, as discussed earlier in example 2. So, same time instant, but this is for the leg. Earlier we had solved for the foot and the ankle joint reaction forces and moments. So, the same time instant as the foot is shown here, the free body diagram of the lower leg. So, the linear and angular accelerations are indicated, and the distances, the linear accelerations are given here in the free body, the angular acceleration is given here in the free body as well, and the distances are in centimeter. Now, as mentioned earlier, if we know the distal joint moments and forces, the net moment and forces can be calculated at the proximal end of the segment or proximal joint, or the joint at the proximal end of the segment. Since we had calculated earlier the ankle joint moments and forces, now we could estimate the net joint forces and moments at the knee joint. So, this example demonstrates the estimation of the net forces and moments at the knee joint based on the prior knowledge of the ankle joint moments and forces. Now, the distal end reaction forces and moments have been reversed because this is a separate lower leg segment, where this is the joint, ankle joint at the distal end. So, according to the Newton's third law, the reaction forces should cancel each other when the two link segments are assembled. Therefore, the Rx1 and Y1 as well as the moment should be in the opposite direction when we consider the attached link, the lower leg segment, as indicated in this free body diagram. The three unknowns that are required to be calculated are Rx2, Ry2 and M2 at the knee joint center. Let us now consider the solution of the example 3. Similar to example 2, we are considering the dynamic equilibrium along the x axis and we write down the equation of motion, summation of Fx equal to m into Ax, the linear acceleration Ax. So, putting the force vectors in the equations, we can actually find out Rx2, wherein Rx1 we had earlier calculated as 8.54 and the Mx1 part is indicated here, 3.72 multiplied by 0.03 radian per second. So, we calculate Rx2 as 8.43 Newton. Considering dynamic equilibrium along the y direction, similarly, we can write down the equation of motion along the y direction, where Ry2, Ry1, the weight of the limb segment, that is the leg segment, is on the left hand side, and on the right hand side we have the mass and the linear acceleration along the y direction. So, putting the values in the equation, we can actually solve out Ry2 as 23.83 Newton. The third step is finding out the moment due to the rotation. So, considering moment about the center of mass of the leg, that is the C, we can form or write down the equation of the moments, and you can see on the right hand side we have the I alpha, the moment of inertia multiplied by the angular acceleration, and on the left hand side we have the moments m1, m2, moments caused due to Rx1, Ry1, Rx2 and Ry2. Considering the free body diagram of the lower limb segment. Now, substituting the values of the M1, Rx1, Ry1, Rx2 and Ry2 in the equation, as well as the I alpha given by 0.0638 as I and alpha already given as 36.9 in the whole equation, we can find out M2 as 2.02 Newton meter. So, we have finally found out the Rx2, Ry2 and M2 at the knee joint center, the proximal end of the lower limb segment, considering the magnitude of Rx1, Ry1 and Rm1 at the distal end, that is the ankle joint center. So, let us now discuss some observation on this example 3. M2 is found out to be positive. This represents a counterclockwise extensor moment acting at the knee. So, this M2 is positive and it is anti-clockwise. So, it is trying to extend the knee. The quadriceps muscles at this time are rapidly extending the swinging leg. This is the physical interpretation of this time instant or the configuration of this problem. The angular acceleration of the leg is the net result of two reaction forces and one muscle moment. So, net result of two reaction forces and one muscle moment acting at each end of the segment. Therefore, there may not be a single primary force causing the movement we observe here. In this case, each force and moment had a notable influence on the acceleration of the lower leg segment. Let us come to the conclusion of this lecture. The musculoskeletal models are reliable tool for the analysis of movements. This we had also observed the same conclusion in the earlier lecture. So, since this lecture is a continuation of the earlier lecture, so we are now drawing the conclusions somewhat together. Musculoskeletal modeling and analysis are commonly based on inverse dynamics method, and we have discussed in detail about this method in this lecture. The inverse dynamics method required kinematic variables as inputs, and the inverse dynamics approach predicts the net joint forces and moments caused by limb movement. The references are listed here based on which the lecture has been prepared. Thank you for listening.